Good morning. Happy Friday, everybody. So I want to do some work today that is helpful for the last homework problem set that's assigned. And we will maybe not do some of these problems completely, but I want to talk about some stuff that is relevant to at least the first half of this problem set that's assigned, okay? And then we'll do this for a while, and then if we have time, we're going to look at rotational inertia in a little bit more detail. We talked about rotational inertia on Monday and discovered what it would be for a point particle, but we're going to take a look and see if we can come up with a general way of calculating rotational inertia for things that aren't points. I guess we would call them extended objects that have mass not at one point. All right, so let's do this. Come on over to my whiteboard. And all right, let me see. Where do I want to start here? All right, how about let's talk about the dynamics of a wheel, or the mechanics of a wheel. Rotating wheels. All right. And what are the characteristics of a wheel? Well, you know, a wheel has a radius. That's a horrible circle. Try again. Well, that's a little better. So a wheel has a radius. Maybe I'll call that little r. And you know, if a wheel is rotating, say it's rotating in this direction clockwise, it's going to be moving in this direction. It's going to have a velocity or a speed, a linear speed. So as the wheel rotates, it's moving down the road, the path, whatever. All right, so it's got a speed. So and its rotation can be quantified as an angular rotation, omega. So omega has units of radians per second. Speed has units of meters per second, and radius has units of meters. Okay, I'll put those in parentheses. All right, so here's your first question. What's the connection between the linear speed, we'll call it V, the linear speed, or we could call it the, a word that you'll encounter in the textbook in this chapter is tangential speed, or tangential velocity. So what does that mean? It means that there's a point on the perimeter of the wheel, and relative to the center of that wheel, it's moving with some velocity, and that velocity vector is tangent to the wheel. It's tangent to the outside of this circle. So it's called tangential or linear to separate it from this new concept, rotational. All right, so what is the connection between omega and V? What do you say? V is proportional to omega, but how are they exactly connected from last time? Who remembers? This little symbol means proportional to, if you've never seen it before. Proportional to. Thanks, Nicole. Nicole's got it. The proportionality constant that makes this proportionality an equation is R. V equals R omega. Okay, so let's see. So what about, let's say you had a problem where, and actually you do have a problem that's like this, where what you know or what you're given is that there's a wheel that over the course of its lifetime has traveled a distance, I'll just make up a number, it's not important, let's say 1,000,000 kilometers. Okay, 1,000,000 kilometers is 1,000,000,000 meters. Okay, so it's traveled that far, and you want to know how well, that's how far the wheel has traveled. That's a linear distance, but you want to figure out, well, how many rotations does that correspond to? How would you figure that out if you know the total linear distance that the wheel traveled as it rolls along the road? How do you figure out how many rotations has been done? Who knows that? And while you're thinking about it, I'm going to make my wheel a little bit more wheel-like. Oh, that was bad. So I got an answer here. Tyler says divide by circumference. Right. So what that is what's the best way to say this? Well, let's just write it out as this. REV for revolutions. REV for revolutions is going to equal the total distance traveled divided by the circumference, which would be 2 pi r. Okay, so another way to think about this would be that delta x is a linear distance or displacement. It's a linear quantity, okay? And the corresponding angular quantity is delta theta, which would have units of radians. Okay, so the connection between the two is r, just like with v and omega, that delta x equals r times delta theta. So if you can see that what this does is it corresponds to our understanding of what circumference is. Let's say delta theta is 2 pi. That's going around once. 2 pi radians is once around the circle. 2 pi times r is the circumference. So the delta x would be equal to the circumference. So this another way to think about this then is if delta x equals r delta theta equals delta x divided by r, and you see that that's in this expression over here. So an equivalent way to think about this is revolutions equals the angular displacement in radians divided by 2 pi, because there's 2 pi radians in every revolution. Okay, so I think, so there's a problem, it's the fourth one in the problem set, which has you think about the connection between linear distance and number of revolutions. So you should nail that now. All right, let's see, what's next? Let's talk about let's talk about a fan or a turbine. Okay, that's another thing that spins. And so you have, a central hub, and then, typically, the big turbines have 3 blades. Big wind turbines have 3 blades, like this. And then they're rotating. So you can imagine, let's think about a situation where the turbine is rotating, let's say this way. Okay, it has some initial angular velocity. It's rotating counterclockwise. All right, but it's slowing down. So the things is that omega naught is some non-zero number. I can just I'll make up a number. How about, it's not important. We're not going to do this whole problem. I just want to set it up. Let's say it's 1 radian per second. Okay? And it's going to come to rest, which means that in the future, its omega is 0 radians per second. That means it's decelerating. It's slowing down its rate of rotation. And if you know how long that took, let's say 20 seconds, then you can figure out the rate of deceleration, which would be alpha. Okay, so if you know the radius, and let me draw it here. If you know the radius of this turbine, it's the length of the blade, you could take all of these quantities and translate them via r into their linear quantities. V naught is going to be r omega naught. V is r omega. Well, that's going to be 0. It comes to rest. T is t. No change there. And then the acceleration is going to equal r times alpha. So just the r is the proportionality constant between these rotational quantities and these angular slash rotational quantities and these linear quantities. So here, the v that we calculate here would be what I was referring to earlier as tangential quantities. All right, so that means that these are, at any moment, let's go over here and imagine there's a point on the tip of this blade. And at that moment in time, it has a linear velocity that's in that direction. And then sometime in the future, it's changed direction. But this A that we're calculating here is not the same thing. Let me write this out. This A, which is equal to r times alpha, is tangential acceleration. It's how quickly a point on the wheel, on the turbine, is slowing down in units of meters per second squared. It is not this, so it is not centripetal. Remember centripetal acceleration? Acceleration. Okay? Those are two separate things. All right, so but you have a problem that I assigned to you, which has you, so let me talk to you for a minute here. So I have this problem that I assigned to you where there's a turbine that's slowing down, okay, and it has you consider a point on the end of a turbine blade, and since it's slowing down, that point on the turbine blade is not undergoing uniform circular motion. Remember, the criteria for uniform circular motion are constant speed and constant radius. So it's a rigid turbine blade, so the radius is a constant, but its speed is changing because it's slowing down. Its tangential speed is changing. So it is not undergoing uniform circular motion, but it is moving in a circle, which means that there must be a centripetal, a center-pointing force. And thus there's a centripetal acceleration. So in a situation like this, when you got the turbine blade that's spinning and accelerating, or decelerating, in this case, there is both a centripetal component, a center-pointing component of the acceleration, and a tangential component to the acceleration. All right, so let's explore this a little bit more, because I think this is one of the more confusing problems in the homework for you guys to work through. All right. Okay, So let's can I salvage any of this? Let's focus on just that one blade. Okay, so we have this one blade, and I'm going to draw it straight up and down because that simplifies our axes. Okay, and then there's this point on the end of the blade, and the things that we know are we know the radius of the blade, or the turbine, R. Let me write these down. So in this problem that I assigned, the things that you know are the initial angular velocity of the turbine. Again, it's rotating this way, counterclockwise. You know how long it takes to slow down to a stop. Okay, I'm not going to write the actual numbers down. Okay, just write these down as knowns, because yours are going to be different. It comes to rest, so you know the final angular velocity is 0 radians per second. Okay, and you also are given the radius of the turbine blade. Okay, there's a little catch here. Okay, and that's when you're given omega naught, it's not in the correct units. What you're given is something like omega naught is 1 revolution per second. 1 revolution per second. So the units that you want are not revolutions per second for omegas, they're radians per second. So how do you convert? How do you go from radians per second to revolutions per second to radians per second? In this case, it's easy because you know how many radians in 1 revolution. That's the key. Anybody know? While you're thinking about that, let's keep going here. So in this problem, the unknowns are the angular acceleration. You also don't know, you want to figure out what the centripetal acceleration is. I'll call that A sub c. And then you also want to know the tangential acceleration. I'll call that A sub t. So what are those? And Holly's got the answer. You divide by 2, well, not divide by 2 pi. Well, depending which direction you're going. But in this case, you would multiply by 2 pi. If you have revolutions per second, you would multiply by, there's 2 pi radians in 1 revolution, and that will cancel the revolutions, and you'll be left with 2 pi radians per second. So in this case, if you're going from omega in revolutions per second to radians per second, you multiply by 2 pi. So this is, let me pause here a second, because this is a little weird, but revolutions and radians aren't real units the way we think about units as being like meters and seconds. How can I explain it? They're like placeholders. They communicate the nature of what's being measured, but they aren't. So it's like okay. So there'll be situations where you're like, where did the radians go? They just like disappear, and they don't really disappear. It's that they were never there to begin with. They're not real units in this sense, but they're very helpful to write out just like units, so that you can remember where the context of what you're studying. So they're like numbers, not quite either. They're like William says they're like numbers. I mean, these are numbers, and they are units of measurement, I guess, but they don't behave in the same way as other units. I'm not explaining this well. Just when we've seen example, I'll point it out if we do. One thing you can think of is when you do the trig functions, like the sine of an angle. um, the you know, if you can't, you can only apply the sine functions to things that are in angular units. It can't have other units. It doesn't work that way. And the reason is because these aren't really real units. Okay, so these are the things that we want to know. And I wrote out, so this wheel is slowing down. So if it's rotating counterclockwise, it's actually accelerating in the opposite direction. So a sub t is an acceleration that's tangent to its path, and a sub c is the centripetal acceleration that's center pointing. So these are two vector quantities, and that means the total acceleration is going to be the vector sum of these two quantities. So if we zoom in on that point on the wheel, and we have acceleration tangential, which is tangent to its path, and acceleration centripetal, the total acceleration is somewhere in the middle. It's the vector sum of those two, and it makes some angle relative to, well, to the turbine blade. It would be theta, like I have here. So we'll find that angle relative to a sub c. So to figure this out, to figure out what these a's are, figure out what the total a is, and this angle, we got to figure out what AT and AC are. They're kind of like, if you imagine this projected on coordinate axes, in this moment of time, it's like having an x component and a y component, AT and AC. So if you find AT and AC, you can find the total acceleration A. All right. Well, this isn't too hard. At least the thing. Well, actually, it's slowing down. So actually, the problem says the centripetal acceleration that you want is the initial. Okay. All right. And that's important. So that's the acceleration that's happening when omega is omega naught, the initial rotational velocity. All right, so let's think about this. Well, let's find alpha first. All right, so if we know one of our kinematic equations of motion is V equals V naught plus AT. So translating that to the angular, putting in these angular quantities for the linear quantities V and A, this becomes omega equals omega naught plus alpha t. So that means you can take the things that you know up here, plug it in down here, and then find alpha. Okay, so you can find alpha using the kinematic equation. So that's the rate of rotational acceleration. It's going to be a negative number. And what does that mean? It just means that if the turbine's rotating counterclockwise, it's accelerating clockwise if you get a negative alpha. And that's what happens when it's slowing down. Its rate of rotation is decreasing. All right, and then once you have alpha, alpha times r is going to give us one of these a's. Which one is it? It's a sub t, the tangential acceleration. Okay, so once we get that, we can plug it in up here, and we get this. Okay, well, what about centripetal acceleration? Well, if you remember, a sub c is equal to speed squared divided by r. And in this case, the v is the tangential the tangential speed of that point on the turbine, this little green point. What's the connection between it and actually I'll put the naught here because they say these initial speed because it's slowing down. And what is that speed in terms of the angular quantities? Well, v is r times omega. So v naught is r omega naught times squared, or squared. So you have an r squared over r gives you 1r omega naught squared. So you can calculate this because you have what you need to plug into that expression. So when you do all this work, now you have AT and AC. Let's go over here. And so AT plus AC is going to equal A total. Well, you know, if I write this in unit vector notation and I use these axes, the x component of the total acceleration is A sub t. And the y component is A sub c. And it's negative because I'm using these axes over here. Okay? And then I can find the magnitude using the Pythagorean theorem. And I can find this angle theta. Let's see. Well, let me draw this a different way so my angle matches up. So you have A sub c added to it A sub t. So tip to tail you have something like that. And now my picture matches my angle in these two places. So the tangent of that angle is AT over AC. So the inverse tangent of that ratio is going to equal theta, the angle. Okay. So let me zoom out here, try to get everything here on the same slide at the same time. It's going to be hard. Okay, and I'll just leave it there a second. And this should be really helpful. Hopefully this is really helpful for solving that problem. Now, you know, just to summarize what's going on here, because the turbine is rotating, it has a centripetal, because the turbine is rotating, it has a rotational acceleration. No, let me back up. Because the turbine is rotating and it's slowing down, it has a centripetal acceleration. All right? Hold on. What's wrong with me? All right, let me try that one more time. Because the turbine is rotating and it's slowing down, it has a rotational acceleration, an angular acceleration, an alpha. That's not zero. All right, it's rotating, so it's sweeping out radians per second, and the rate at which that's happening is slowing down. So that means it has an alpha that's non-zero, and it's negative in this case because it's slowing down. All right, because the point on the end of the turbine wheel is rotating, it experiences a centripetal force, a center pointing force, and thus a centripetal acceleration. So the total acceleration that that point experiences is the vector sum of the part that's center pointing, the centripetal acceleration, and the part that's tangent to its circular path, the linear acceleration or tangential acceleration, which is a function of the angular acceleration. So that's what this problem's doing. It's combining all these things together. Yeah, clear as mud, especially when I excel at muddying the waters like I just did. All right. If you got questions, put them in the comments. And I want to move on to it. Let's put this stuff aside for a while. Let's move to a different topic. All right. So we're gonna remember, you know, we were working through some of these ideas on Monday. This concept of rotational inertia came up, and I said, well, in rotational mechanics, this quantity I, rotational inertia, plays the role of mass in linear mechanics. And we derived what this this quantity is for a point mass. So let's think about what it will be for things that aren't point masses. You know, things like wheels and turbines, they're not point masses. They have mass spread out. Okay, they're extended objects. All right. Oh boy. So let's see. All right. So let's call this work rotational inertia. I don't know why I prefer the word rotational inertia to moment of inertia. I think it's more descriptive and less confusing. Moment is sort of jargon. So rotational inertia of non-point masses. Okay, or we can call these extended objects. Okay, so last time we discovered that this expression fell out of our analysis, just fell right onto our laps, that the rotational inertia for a point mass should be mr squared. Okay, so you have a little mass that's located some distance r from a point that's the axis of rotation, so it's rotating around that point. So things like planets orbiting stars. Planets aren't point masses, but you can actually approximate them as point masses pretty well if you want to understand the dynamics of orbits, because they tend to be spherical, and their radius is much, much smaller than their orbital radius. So their radius doesn't matter much. But for a situation like, well, let's say you have a wheel, like an actual wheel, and the wheel has rubber on the outside. Don't try to use a wheel that looks like that. Get your money back if your wheels look like this. But this wheel has mass everywhere. Okay, so there's like a little piece of mass here, a little piece of mass here, a little piece of mass here, and you could like you could do something called discretization, and you could say, well, each one of these, so I'll label these. This is like little piece mass 1, 2, 3, 4, 5, 6. And you could say, well, the total inertia of this rotating body is the contribution. You could treat each of these little pieces as like little point masses. Okay? You could just add them all up. All right? But there's an infinite number of them because these are infinitely small, little tiny chunks of the wheel. So a better way to think about this is to say that each of these little tiny, here I'll draw a new one, each of these little tiny pieces of mass is an infinitesimally small piece of mass, dm. In which case, you see where I'm going? Maybe you do. Some of you do. The rotational inertia for this thing would have to be an integral over the little teeny tiny little bits of rotational inertia for each of these little dm's. And each of these little tiny bits can be approximated, I'll write it this way, the r squared first, as a point mass. So if the rotational inertia of a point mass is mr squared, the rotational inertia of one of these infinitesimally small chunks of this larger object is dm r squared, or r squared dm, put the dm last, where dm is this little tiny piece of mass. And then to figure out the total rotational inertia, you just have to integrate over all of the dm, all of the little tiny chunks of mass. Okay, you got to add them all up. So here's a more general way of expressing rotational inertia. All right, and as an integral, let's do an actual example. All right, I think we have time to do this. All right, so let's think about, let's call it a long, thin, so its thickness doesn't really matter, or width doesn't matter. Uniform, that means it has the same density everywhere. Rod, I think of like a meter stick, long, thin, uniform rod that's rotating about an endpoint. Okay, and so this, when you think about rotational inertia, you look at these formulas, what you find is that the answer that you get depends on the r, and the r is the distance from the axis of rotation, which means that if you have an object and you just change where it's rotating, you know, it's rotating on its midpoint instead of its endpoint, you completely change the rotational inertia. All right, you guys can experiment with this. If we were in class, like in person, I would show you guys and let you feel this for yourselves. Okay, so let me explain how you can feel this difference, and then you can try to find what you need to do it. So what you got to do is go find yourself a meter stick, and it could be a broomstick, you know, basically anything that's sort of long and uniform, and then put it in your hand so that the midpoint of the meter stick is in your hand, and just kind of hold it like this and try rotating it. Okay, just rotate your wrist like this. All right, and then move your hand to the end and do the same thing. All right, try this, experience it, and see how those two situations feel different. And the reason they feel different is you're trying to generate rotation of the same object, but about different points. So the axis of rotation is different points. And that means the rotational inertia, and inertia is resistance to changes in motion. The rotational inertia is different in those two cases. In one case, it's a lot more. The rotational inertia is a lot more than the other case. So if you do that, you know, rotate the meter stick about its midpoint and then hold it at the top and do the same thing, you will feel which one of those scenarios is harder to cause rotation with. That's because rotational inertia is so much greater. All right, so rotational inertia depends on the position of the axis of rotation. But for this case, we have a long uniform rod, so like a meter stick, that's rotating about an endpoint. So this is the axis of rotation, AR for short. So the meter stick has a length, call that L. And the meter stick, you know, I'm going to do some things which might seem like superfluous in the moment, but you'll see why this is important. Meter stick has a mass, and since it's uniform, it has a mass per unit length, so the ratio of the mass divided by the length, that would have units of mass kilograms divided by length, which would be meters. Okay, units, so it's mass per unit length. And that is not, it's a density. It's not the density that we typically think about, where it's like kilograms per cubic meter or something like that, or kilograms per liter. But it's a density. I would call this, I'd give it the symbol lambda, and we'll call it a linear density. Okay, it's mass per unit length. All right, so I'll just define that because it's going to come in handy, and you'll see in a minute. Okay, so each of these little teeny chunks of the ruler of this long uniform rod has a little mass called dm, and it also has a little tiny length. I used L here, but I'm going to use R, and you'll see why. So it has a little tiny width, dr, and positionally it's at some distance r from the axis of rotation. Okay, so there's a little tiny chunk of mass, and then there's a bunch of them. There's one, there's an infinite number of them all along the length of this long uniform rod. So to figure out the total rotational inertia, what we got to do is we've got to use this expression to integrate all these little tiny pieces of mass, all these little tiny dm's, from the axis of rotation, the 0 point, to where r equals the length of the rod. So this integral becomes something like this. The limits of integration are 0 and L. So what's the problem with this integral as it sits right now? Does anybody know? I know we're jumping into integration. I wanted to do more of this here at the end of the semester because I want you guys to have a better, a little more experience, a little bit more application of integrals before you get the second semester. But what is the problem? Indefinite? Well, it's not indefinite, Bob Withers. Because we have limits of integration. Okay, the limits of integration are distances. The 0 is the axis of rotation, and the L is the endpoint in the other direction. Okay. So if there's infinite dm's, what do you put for r? Well, so r, so r isn't a constant. Now you're you getting it. So r isn't a constant. All right, r is the thing that we're integrating over, but there's a disconnect. You see, because in our integrand, the dm, it looks like we're integrating with respect to mass, but the r isn't constant. We're integrating with respect to r, and that's what the limits of integration are. They're two different values of r. So I don't know if you've done this before, but what this means is you got to do a change of variables. All right, and so this is why I took the time to define this mass per unit length. So if we have the linear density is mass per unit length, well, what's the connection between dm and dr? They're proportional to one another, and the proportionality constant is lambda, the density. dm, the small amount of mass, would equal mass per unit length times the small amount of length, the dr, the small thickness. So you can plug that in up there, which will give you I equals the integral from 0 to L of r squared. And now instead of dm, we have lambda dr. And the lambda is a constant. It's because it's a uniform rod. So we can pull that out in front. And now we can do this integral because we're integrating with respect to r instead of dm. So what's the integral? It's just a polynomial, a monomial, just one term. In the integral of r squared, you increase the exponent by 1 and then divide by the new exponent. So you get 1/3, and then you got to evaluate on this interval 0 to L. Okay, So that's going to be equal to lambda times 1/3 L cubed minus 1/3 0 cubed. And that's, of course, 0. So you get I equals 1/3 lambda L cubed. But lambda is m over L. So one of these L's cancels. And you're left with ml squared. All right? So the rotational inertia of a point mass is mr squared. The rotational inertia of a long uniform rod is 1/3 times its mass times its total length squared. So you still see this this connection between the units are going to be the same. You have a unit of mass, kilograms, and a unit of distance squared. So it's going to the units are kilograms meters squared for rotational inertia. But you have that coefficient 1/3. And if you move the axis of rotation to the center, you'd get a completely different answer. All right, you could try this. And so here's a big useful tool for us, though, is that if you have this long uniform rod and it's rotating about its center, that's essentially like two smaller rods rotating about their endpoint. Okay, so like a turbine is just 3 of those then, if it has 3 blades. And rotational inertias are additive. So, I mean, that's the essence of why you can do this integral to begin with. So if you have like a fan with 4 blades, if you figure out the rotational inertia of one of those blades using this formula that we just found, and that would be an approximation because this is for a long, thin, uniform rod. Well, fan blades, are they long and thin? Well, they're longer than they are thin, so it's probably a good approximation. But if you use this formula, which is reasonable, to find the rotational inertia of one blade on a fan, just multiply it by how many blades you have. 3, 4, whatever, to give you the total rotational inertia. All right, so we'll do more practice like this. I find these integrals so fun. I love changing variables. It's, I don't know, it's I remember doing this in senior year in high school, in calculus and in my AP Calc and AP Physics class, and I was like, this is like witchcraft. I felt like I had discovered witchcraft when I started to do calculus, and it's just amazing stuff. All right, well, that's it for today. So I will see you guys. I'll see you guys on Monday, and we'll continue with our discussion on rotational mechanics. And then that next week, well, we only have 4 more class periods, like real class periods. Okay, next week we got 3, and then the following Monday. So I hope. I'm really behind on grading. I got your exams to grade. It's just, I don't know. I just have a lot. I'm trying. I'm really trying to turn your grades around. But you have. I think you should have a good. Before, definitely after Thanksgiving, you'll have a really good idea of what your grade is going into the final. All right. So I'm working on it. I'll get it turned around. All right. Then I'll see you guys on Monday. Have a great weekend. All right? Take care. Bye-bye.